An integrated rate law is a little bit different from a differential rate law. You need one experiment per reactant. And as you can see below, what you do is you set up your experiment so that you're only studying one reactant at a time. Okay? You set it up so that the concentration of all but one of your reactants, I should say, one of your reactants, its concentration will change significantly over time. For the other reactants, the concentration will not change significantly over time. They're not actually infinite. That's not physically possible. They're just so large that the amount they change won't be very significant. Now, what you do then is you let the reaction run and you measure the concentration of that particular reactant as the reaction proceeds. Then you have to do some math. And I've kind of debated whether or not I want to show you the math that's going on behind this, and I just ain't gonna do it. Instead, I'll show you the results of the math. Okay? There's no need to go into calculus on this. We're just going to leave it with algebra. Okay? If it's not algebra, I ain't gonna show you. So the way this one works, if you're doing any sort of experiment, that is that you measure the concentration of your reactant and over time. Okay, you're just measuring it at discrete intervals, and you get your computer to do a little bit of math for you. So you just make two more columns, one for the natural log of the concentration, and one for 1 over the concentration. Okay, so now you have three different things that you can plot against time. Okay, the concentration itself versus time, the natural log of the concentration versus time, and 1 over the concentration versus time. This is just, the reason they call it the integrated rate law is because this is what comes from taking the integral of 0, first, and second order equations. Okay? And all you're doing here is you're looking for the straight line. Okay? You plot your concentration, log of concentration, 1 over concentration versus time. One of those three is going to be straight. The other two will be curved. So when you actually graph them out, or you let your computer do it for you, you get, in this case, 2 curves and a straight line, and we see that natural log of concentration is the straight line. The other two are curved. And that means that for this particular random, completely made-up thing, A is first order. Okay, we don't know about B or C. But that's really all it takes for the integrated rate law, is you let the reaction run, the computer automatically collects the data for you, then the computer does, hundreds of calculations for you to come up with natural log and 1 over concentration of A, and then the computer does the work of graphing it for you. All you have to do is look at the pictures and see which one is not curved. And that's why we do that. When you have difficult stuff, it can make things a lot simpler. But what I've told you here only works for 0, first, and second order. But they are really, really simple. Okay, if the graph of concentration versus time is straight, then it's 0 order for that reactant. If its natural log versus time is straight, then it's first order. And if it's 1 over concentration versus time is straight, then it is second order. And that's really all there is to it for your integrated rate law. Let's move on to something where I might have to show you some math. Now, the half-life of a reaction, half-life of anything, is how long it takes for half of the original quantity of substance to disappear. So you can measure half-lives for different things. So radioactive decay will have a half-life. Carbon-14 decays at a rate of, with a half-life, I should say, of 5,280 years, roughly. So if you have 1 gram of C14, it takes a little over 5,000 years to decay down to half a gram. Then another 5,280 years to decay to a quarter of a gram. Okay? Half-life, doesn't matter how much you have really. It's asking how long till you get to half of whatever you start with. Reactions, you can also talk about half-lives. And unlike radioactive decay, you get different sorts of half-lives because you have different sorts of reaction orders. I will not show you here how these half-lives are derived, but those derivations are shown in the textbook, so you can look there for those. I'm just going to show you the results and expect you to understand the results and some of their implications. So, when we look at half-lives, what do we see? Well, we have 0 first and second order reactions, and we have their half-lives. So for a 0 order reaction, the half-life, T1/2, is equal to A naught, or concentration 0, whatever your initial concentration is, over 2K, where K is the rate constant. For first order, T1/2 is log 2, natural log, I should say, over K. I might make that mistake a lot. Natural logs show up an awful lot as a consequence of math and the fact that space is non-directional. So you get lots of circles and spheres naturally occurring in reality. And so you get lots of cyclical things, and you get lots of natural logs. Those show up much more commonly in the math than log base 10. So a lot of the time you just get into the habit of talking about natural log as if it were the only real log, as if it's the only log that mattered. So I apologize if I make that mistake, but T1/2 equals natural log of 2 divided by K. And for second order reaction, T1/2 is 1 over A naught K. Okay. These give some interesting looking results. Now, for all three of them, you are dividing by the rate constant. So whatever your rate constant is, you're dividing by that. And a bigger rate constant means a smaller half-life, or a shorter half-life. We're talking about time. So, well, that makes sense. A big rate constant means your reaction is going quickly. So a bigger rate constant means a shorter half-life, regardless, full stop. Now, this next thing is a little bit stranger. For the first order reaction, it doesn't depend on how much stuff is present. The half-life will always be the same, just natural log 2 over K. But concentration does have an impact on the half-life for a 0 or a second order reaction, but in opposite directions. A larger quantity of stuff being present will give you a longer half-life for a 0 order reaction, but a shorter half-life for a second order reaction. That's because of the way that the rate of reaction depends upon concentration. For a 0 order reaction, the rate of reaction isn't affected by the amount of stuff present. So if you have more stuff present, the reaction will proceed at the same pace. So more stuff present means it'll take longer to get rid of half of it. Okay. If you're going, if you're losing, 2 grams per second, then it'll take you 2 seconds to get rid of 4 grams. And if you have 2,000 grams present, right, it'll take you a lot longer than that to get rid of 1,000 grams, right? For a first order reaction, the reaction rate increases directly with the concentration. So having more stuff present will increase the reaction rate. Having less stuff present decreases the reaction rate. And the overall effect of that is that the half-life stays the same regardless of how much stuff is present. Okay, it's a nice smooth curve. For a second order reaction, the reaction rate increases as the square, not just directly, but as the square of the concentration. So having more stuff present means the reaction rate has gotten even bigger, even faster. So you have a shorter half-life as you have more stuff. The reaction slows down more as you get less stuff present. So those are just some of the different effects you can get with different reaction orders. And that is what we're going to do with that. And you might see some half-life questions, maybe not half-life math on tests. So, moving on from half-life to something that definitely, absolutely does not cover any sort of math. Collision theory. This is a physical, kinetic explanation of reactions. Okay? So, for a reaction to occur, the reactant molecules must collide with sufficient energy and in the appropriate orientation. Okay? All three of those are vital. I'm hoping that that they have to actually collide is obvious, and that the sufficient energy is also obvious. The orientation bit might not be obvious. That means that they need to be oriented correctly in space. And to explain that, I'm going to go ahead and hop ahead a slide to talk about the activated complex. So when a reaction occurs, you do not take apart the molecules. You instead form the activated complex. Okay, you break bonds and form bonds all at the same time in order to form what is known as the activated complex. Okay? So let me show you with the reaction of carbon dioxide and water. Okay? So here we have CO2 and H2O. They will react, when CO2 dissolves in water, they'll react to form carbonic acid, H2CO3. Now, what does not happen, you do not break all the bonds to get a little pile of atoms that then form new bonds in the shape of the new molecule. That is absolutely not what happens. I'm showing that to you here, but it is not what happens. Okay, if that were the way things worked, the activation energy, the barrier in between reactants and products would be whoosh. We're talking Mount Matterhorn, Mount Everest. Super duper ridiculously tall mountain. Okay, it would be impossible for reactions to occur. Instead, you get an activated complex, where bonds are broken at the same time that bonds are formed. So, in this particular case, the water comes in sort of sideways to collide with the carbonic acid, with the carbon dioxide. Okay, and you see that the two oxygen atoms of the carbon dioxide molecule are sort of being pushed outward. So it was in a straight line. Now it's sort of in a V. At the same time, one of those bonds is going from a double bond to a single bond. Okay, the carbon-oxygen bond there on the right it's sort of dissolving. And, okay, you're getting a new carbon-oxygen single bond being formed between the carbon and the oxygen of the water. While that's happening, you're breaking apart. One of the oxygen-hydrogen bonds is dissolving and going away, and you're getting a different oxygen-hydrogen bond over there on the right-hand side. Okay, the oxygen that was double bonded to the carbon, while it's losing that, while it's becoming a single bond to the carbon, it's getting a new bond down onto the hydrogen. Okay, and that's the activated complex. Okay, it's this big ugly molecule where bonds are breaking and forming all at the same time. It's called activated because it is a high-energy thing. It's an unstable sort of arrangement. It will either fall apart back into the reactant molecules, or it can snap into the products, or in this case, just the single product molecule. Okay? And that is what an activated complex is. That's what exists there at this peak here of the reaction coordinate. Okay, the peak of the activation energy is where the activated complex is. It's higher energy than either of the reactants or the products, but it's nowhere near as high energy as it would be if you tried to break apart all the bonds and then form new bonds. Okay. So going back to collision theory, that's why you need the appropriate orientation. And this gives us a couple of different ways that catalysts can work. One of them is that they can make it easier for molecules to collide in the appropriate orientation. It might be that they get stuck on the surface of a catalyst, and that can also change other things about them, but they might get stuck on the surface of the catalyst, and that makes it easier for something to come in and strike it at the right angle. Another way that catalysts might work is that they might change the molecular structure. They might bend it or warp it. Remember that the CO2 in the activated complex, okay, those two oxygen atoms had to bend backward. Well, that might be something that starts happening thanks to a catalyst. That's one of the theories about protein enzymes, biological catalysts, is that in addition to capturing the biological molecules they're going to act on, they also stretch and warp them to make the ensuing reaction even easier. Okay. They can also do a lot of electrical changes. The interior of a protein's active site, or an enzyme's active site, is usually highly charged with positive and negative charges in various ways, and it's believed that that might be one of the things that makes them act as a catalyst. In any event, we're a little over 15 minutes, and that's all I want to go into for that. I'll see you again in Lecture 4.